Oh, you are really study hard. We're diving straight into the heart of building a Python-based image recognition system. This isn't just about theory, it's about getting your hands dirty with code that actually sees and classifies images. We'll cover the essential steps from data to deployment, focusing on the core concepts you need to know. Why are we even talking about image recognition? Because it's everywhere, and it's fundamentally changing how we interact with technology. Think about self-driving cars needing to distinguish a pedestrian from a lamppost, or AI analyzing medical scans to detect anomalies earlier than human eyes might. The sheer volume of visual data being generated daily is staggering, and the ability to automatically interpret this data unlocks massive potential for efficiency gains, personalized experiences, and entirely new business models. It's not just a cool tech trick, it's a cornerstone of modern AI research and development. Understanding its principles is key to staying relevant in many fields. So, what exactly are we aiming to achieve here? Our scope is focused. We'll start with the fundamentals of basic image classification. Think classic examples like distinguishing between cats and dogs or recognizing handwritten digits, the kind of problems that really get you comfortable with the core concepts. The goals are clear. First, to walk through the entire workflow, from raw data to a trained model. Second, to actually implement key algorithms and techniques, not just understand them theoretically. Third, to rigorously evaluate how well our model performs. And finally, to give you solid, hands-on experience with the powerful Python libraries that make this all possible. It's about building a strong foundation. Let's talk about the tools we'll be wielding. Python is our primary language, chosen for its vast ecosystem and readability in the data science and AI world. For the visual heavy lifting, we'll use OpenCV, an incredibly powerful open-source library specifically designed for image processing tasks. Then, for building the brains of our system, the neural networks, we'll leverage TensorFlow and Keras. These frameworks abstract away much of the complexity, allowing us to focus on designing effective models. Depending on the specific needs, or if you want to explore alternatives, PyTorch, Scikit, Learn for traditional machine learning, and NumPy and Pandas for data manipulation are also part of the standard toolkit. Now, let's address the most critical component, data. As the saying goes, garbage in, garbage out. No amount of fancy algorithms can compensate for poor quality data. We'll explore various sources, including readily available public datasets from places like Kaggle or the massive ImageNet, but also touch upon creating your own custom datasets when necessary. Crucially, we'll cover pre-processing resizing images to a consistent size, normalizing pixel values so the model isn't biased by lighting conditions, and potentially using augmentation techniques to artificially increase the diversity of our training data. Finally, splitting the data into training, validation, and test sets is vital for realistic evaluation, and ensuring accurate labels is paramount for supervised learning. How do we build the actual brain that recognizes images? We use neural networks, inspired by the structure of the human brain. At their core, they consist of layers. An input layer where the image data comes in, one or more hidden layers where the magic happens, and an output layer that gives us the final prediction. Activation functions like ReLU or sigmoid are crucial because they introduce nonlinearity, enabling the network to learn complex patterns. For images, we specifically employ convolutional neural networks or CNNs. These are particularly effective because they can automatically detect important features like edges, textures, and shapes directly from the pixel data, mimicking how our visual cortex works. Once we have the architecture, how do we teach it? This is the training phase. We define a loss function, which quantifies how wrong the model's predictions are compared to the true labels. A common choice for classification is cross-entropy loss. Then, we use an optimizer, like ADAM or SGD, which acts like a teacher, adjusting the model's internal parameters, weights, and biases to minimize this loss. Training happens iteratively, over multiple epochs, where each epoch involves feeding the model data in small chunks called batches. A major challenge is balancing model complexity. Too simple, and it underfits the data, failing to learn the underlying patterns. Too complex, and it overfits. Memorizing the training data but failing on new examples. Finding that sweet spot is key. After training, how do we know if our model is actually any good? We need robust evaluation metrics. Accuracy is the simplest, the percentage of correct predictions. But it can be misleading, especially with imbalanced datasets. That's where precision and recall come in. Precision measures the proportion of positive predictions that were actually correct. Recall measures the proportion of actual positives that the model correctly identified. The F1 score provides a balanced measure combining both precision and recall. Visualizing results with a confusion matrix is also incredibly helpful, showing exactly where the model is making mistakes, which is crucial for debugging and improving performance. What we've built is just the beginning. Image recognition opens doors to far more complex applications. Object detection goes beyond just identifying what's in an image to pinpointing where it is. Segmentation takes it further, classifying every single pixel in an image. We can also leverage transfer learning, using models pre-trained on massive datasets like ImageNet as a starting point, drastically reducing training time and improving performance, especially for smaller datasets. The real-world impact is enormous. Think autonomous vehicles navigating streets, AI assisting radiologists in spotting tumors, personalized shopping experiences in retail, or enhanced security systems. The possibilities are expanding rapidly. You've now got the blueprint for building a basic image recognition system. This is a significant milestone. However, the field moves incredibly fast. Keep learning, experiment, and push the boundaries. Explore advanced topics like deeper architectures, generative models, or even combining vision with other modalities. The journey of mastering visual AI has just begun.